Hello, everyone. This is Professor Ma, and this is the sections, the introduction of the sections on conservative fields, potential functions, and path independence. In particular, we'll do this in the two-dimensional versions. Okay. We have a theorem about partial derivative of nice functions, uh, z equal to two variable f of x, y, over simply connected domains. Okay, so here's simply connected. Okay, and so in particular, we have a theorem says basically says that we have a two variable functions in x y. If the partial derivative exists at a point at a neighborhood of a point, and the partial derivative are continuous around the neighborhood, then these mixed partials are equal. Okay, for most elementary functions, this comes out to be this. And then on the other hand, we have let's say these kind of functions are, we call them nice functions. Okay. On the other hand, if I given a function in two variables, I can obtain a two-dimensional vector fields from that function, namely the gradient functions. Okay, partial x, partial y at each point. So the gradient is a vector field, and these gradient fields are what we call conservative fields. I mean, if I write down a general vector field F is equal to G f of xy. Let me write this simpler. In general, a vector field is just some functions f at a point P, I components, plus some function g at a j components. And there's no guarantee that this vector field came from partial derivatives. So how can I tell that these functions actually came from partial derivative of somebody, some f, and it's a gradient of some function f? Well, the mixed partial of f has to be the same. In other words, in order for these functions, for this vector field to be conservative, I must have, the condition I must have is the partial derivative of these respect to y must be equal to the partial derivative of this one. Okay, I'm saying in general f of g, f and g. So here we go. So if I'm given a vector field, how can I tell this is the uh, gradient of some functions p? Well, I have to check the partial derivative of the first of the I components respect to the y is equal to the partial derivative of the j component respect to the x. In other words, the original partial for the p, the mixed partial x, y, y, x, have to be the same. For example, okay, I can show this is a conservative field. How? This is the I components. So take this respect to partial respect to y. And this is the j component, take the partial respect to x. And show they're equal. If they are equal, then you can find a original potential function pxy whose partial derivative is respect to x is going to be this, and the partial derivative of the potential function f is y respect to y is equal to that. And the check is fairly easy. Just take partial derivatives. Partial derivative of f and partial derivative of g respect to y or x respectively, they are the same. So this is a conservative field. Now, how do we find the potential functions? We do it by integration, going backward. How? Here we go. So we're going to find a potential function such that whose gradient field is equal to this vector field capital F. We'll go backward like this. Xy squared for the I component must be the partial derivatives with respect to x. Came from the partial with respect to x. So I integrate these xy squared with respect to x. And treat the y as the same. Okay. So I integrate that with respect to x. I will get x squared, y squared over 2. And plus something in y, because when I take the derivative with respect to x, all the parts with respect to y will drop out. Now I know partially what this potential function p looks like. Now the partial derivative of this, remember this gradient is the field f. So if I take the partial derivative with respect to y, I should get the j component. So therefore, I'm going to look at the j component, which is this. Oops, for the field f, and that's supposed to be equal to the partial derivative of this respect to x. So I take the partial respect of this respect to x, and that's going to be x squared times y, 2 comes down, cancel with half, so the y is x squared y, and then the partial with respect to y of cy is partial respect to y. And then I compare this g, which is from here, and with the partial of this with respect to y, partial p, partial y, and these two are supposed to be the same. So that tells me this has to be equal to that after canceling. So I know what the partials of respect to y of c is. Then integrate these respect to y, I get what c is supposed to be. That's y squared over 2. Put the function c back into the p, then I get the function, I recover the functions pxy up to a constant. Okay, so the trick's very easy. If you recover the relationship by integrating with respect to one variable, you get partial solutions of the potentials. Then you take the partial solution of the potential, take the partial derivative of that with respect to the other letters, and it's supposed to be equal to the other component functions. Okay. So if a field is conservative, we can do this integration process to find what the potential function is. Okay, so here is the fundamental theorem of line integral for conservative fields. Okay, so we have a conservative fields over a nice domain, and we have a potential function whose gradient is the capital F. In other words, so let me remind you again. The potential means P del P is going to be equal to F, okay, which is equal to Pxi plus P partials by Yj. Okay. If such is the case, and suppose I have a path inside this domain, D, from one point to another point, like this, then the line integral over this path turns out to be just like definite integral. We just evaluate these points at P. Okay, one more time. If I want to find out the total works that's done over these conservative fields, vector field, I have a potential function P of x, y, and give rise to these vector field. Okay, and then to figure out what the total works is, all I have to do is plug it in m points of the path into the function and subtract. So it's kind of like evaluating definite integral. You plug in one point, subtract, plug in the other point. So this is why we call this a fundamental theorem of line integral. Okay, so let's use the example we just did. Finished for the potential function. Let's find out what's the line integral from one point to another point. Okay. So we found, so this is the vector field from previous examples, and we found that this is the potential functions, and the question is find the works or find the line integral of the vector field over this curve. This curve is from pi over 2 to pi. If you think about it, it's quarter of a circle. Okay. But since this vector field, the vector fields, I don't know what it looks like. It's acting on this curve, and we traverse from one point to another point, and the work is done. Is these, but by the fundamental theorems, because this is a conservative field over here, F, I can plug these points, m points, into the P and subtract the result. Okay, so plugging pi over 2 and pi, and subtract the difference of the m points while plugging into the potential functions, and then this come out to be minus half. And so these give a very fast way of calculating line integral if the field is a conservative field. And in particular, a consequence of these theorems is that in a conservative field, this is not for you. In a conservative field, if I have a loop like that, then the line integral over the loop will be 0, because the point I start and the point I end is the same point. So if I want to find out the works on these, I start with the points, I go around the curve and come back to exactly the same point, then I plug in the same endpoints and subtract, I get 0. Okay, so this basically in physics, basically saying that, for instance, if you drive a car on a mountain path and you go uphill, then loop around, then you come back down, you go downhill, so you come back to the same spot, and then the total work around that loop is 0. Going uphill, the amount of work is the same as the work that it takes for coming downhill. They cancel it out. And that's what a conservative field and potential functions are nice in these situations. Okay, that's that. And see you next time. Bye-bye.